Hello and welcome to another geometry lesson by eMath Instruction. My name is Kirk Weiler and today we'll be doing Unit 7, Lesson 10 on the medians of a triangle. Alright, so without further ado, let's jump right into this because you probably don't know where I'm going with this, right, with the medians of a triangle. We talked about what a median was way back when, and we've seen them a little bit here and there in geometry proof, but it's been a while since we've really even discussed them. So let's talk about what a median is, right? Recall that a median is a line segment drawn from a vertex of a triangle to the midpoint of the opposite side. When the three medians of a triangle are drawn, they have a remarkable property. All right, so let's take a look at that in exercise number 1. In the image below, the midpoints of the sides of ABC have been marked. Letter A, draw each of the three medians of the triangle. All right, this is a piece of cake. Pause the video right now and draw the three medians. In other words, draw a line segment from A to E, from C to D, and from B to F. Pause the video now and go ahead and do that. All right, let's go through that. Real simple, right? I mean, this isn't difficult. We're just drawing some line segments. It shouldn't be difficult. There we go. So here's the median drawn from A to E. Maybe I'll make this a little bit smaller. If I don't get really thick line syndrome here. Let's now go from C to D. And let's now go from F to B. Okay, so one of the most remarkable things about the three medians of a triangle is that they are a point of concurrency, right? What do you notice? The three medians of a triangle all intersect at the same point, right? So they all intersect at the same point. And that is kind of remarkable. There's no real reason why they should have to do that, right? It could be that two of them intersect over here, another two of them intersect over here. Maybe they intersect in a way that forms some kind of other triangle inside of here. But no, all three of them intersect at the same place, and that's called a point of concurrency, right? We saw that earlier this year, right? We saw that the perpendicular bisectors of all three sides intersect at the same point. We saw that the angle bisectors of each angle intersect at the same point. We saw that all the altitudes intersect at the same point. Those are called the points of concurrency. And let's label this point of concurrency, I can almost not say that, as point P. All right. Now, keep on going. Letter D, measure the lengths of CP and PD in centimeters. All right, so take your ruler, all right, measure the length of CP, measure the length of CD, and throw them in here. Now these measures are going to vary a little bit depending on how much your worksheet has been enlarged or shrunk, how much it's been dilated, all right? But what I see is that CP looks to have a measurement of about 4.2 centimeters. Okay, and if I just move my ruler on over, I see that the length of PD is 2.1 centimeters. And what you probably noticed there, right, is that the ratio of CP to PD is 2 to 1, right? CP is twice the length of PD. Now you might say, okay, well, yeah, sure, whatever, but let's take a look at letter E. Use your compass to show that each of the other two medians is also partitioned into a 2 to 1 ratio. All right, so again, notice this, right? If I start at the vertex point of the triangle and I go to that point of concurrency, that is twice the length from the point of concurrency to the median. I claim that that is always true, and you can see it really well with a compass. All right, let me show you how. I'm going to take my compass And I'm going to put the point at P, and I'm going to stretch it out a distance equal to the length from P to E. I just want to make sure I get that length as accurate as possible. Okay, so I'm going to measure that length. All right, that wasn't great, but it'll get the job done. And now what I'm going to do is I'm going to flip my compass around, and I'm going to make the same arc right here, and then I'm going to move it up here. There we go. And make the same arc there. And look at that, right? I don't need to know what the length of PE is. What I can tell for certain is that the length of AP is twice the length of PE. All right? You try the same thing on segment CD. See if PD gets reproduced twice down here on CP. Oh, actually, we already did that one with the measurements. I'm sorry. I'd like you to do it on BF. All right, let's do it. So again, what I'm going to do is I'm first going to simply figure out what the length, or not what the length, but I'm going to mark the length of PF. Now I'm going to flip my compass around and measure it like that. Come on. And oh, this one's a little bit off. And no, I don't want that. And that. That should be exactly 2 to 1 again, but I think my location of P is a little bit off there. All right. But what a cool property, right? When I draw the 3 medians in, what I will always have is a 2 to 1 ratio on the partition lengths from the vertex to the partition will be twice as long as from the partition to the median. And it doesn't matter which one, right? 1, 2, 1, 1, 2, 1, right? And this will be always true of the medians of a triangle. The 3 medians of a triangle intersect at a common point known as a point of concurrency. We've seen that terminology before. This point is called the centroid of the triangle and partitions each median into a ratio of 2 to 1. All right, and you can really think about this going back to our directed line segments, right? If you think about the median as a directed line segment from the vertex to the median, right, then our partition point, right, partitions it into sort of vertex to partition point to midpoint into 2 to 1. This remarkable property of medians of a triangle will be proven in the next exercise, not surprisingly, by the use of similarity. Right? Of course, we're in the middle of the similarity unit, so that's where this should show up. Let's take a look at why this remarkable property occurs. Exercise number 2. In triangle ABC, the midpoints of AB and AC are D and E respectively. Medians BE and CD intersect at centroid point P. The third median is not drawn and it doesn't need to be drawn. Points D and E are connected with segment DE. Give 2 ways that segment DE and BC are related. See Unit 6, Lesson number 5. All right, well, see if you can remember. We did a lesson back in Unit 6, okay, which was our unit on quadrilaterals, strangely enough. But we did a lesson back in Unit 6 where we connected the 2 midpoints of sides of a triangle, and we found that that side, and we proved that that side had 2 remarkable properties compared to the third side whose midpoints weren't drawn. See if you can remember the 2 ways that DE and BC are related. All right, well, number 1, DE was parallel to BC. And that seems pretty obvious when you look at the picture right now, right? But we proved that way back then. And the other piece was that BC was twice the length of DE. I think back then we were saying that DE is half the length of BC, but whatever, right? So remember, the segment that connects the 2 midpoints is parallel to the third side and half the length of the third side, or the third side is twice the length of that. Now let's get some similarity involved. Letter B. Give an argument for why triangle DEP must be similar to triangle CBP. Wow, that's a mouthful. But let's make sure we know the two triangles, right? This particular triangle, right, DEP, and this particular triangle CBP, I claim must be similar. Think about why that's true, and you may want to just go to this. All right, pause the video now. All right, well, let's get this down. Since DE must be parallel to BC, what's got to be true? Well, parallelism is all about angles, right? So that means that this angle must be congruent to that angle. Let me write that down. So angle EDP must be congruent to angle BCP. And angle DEP must be congruent to this angle, right? To angle PBC. So triangle DEP, DEP must be similar to triangle CBP by angle. Remember when I said that angle would be the one that you use the most often? Well, here it is again, right? Now, keep in mind, right, these two triangles are similar, but as always, similarity is a little bit tricky to see, right? D corresponds to C, E corresponds to B, and P just corresponds to itself. Now, let's go here. Letter C. Prove that BP equals 2 times PE, and likewise CP equals 2 times PD, i.e. the 2-to-1 partitioning ratio. So remember, what I was trying to prove was this remarkable property about medians, right? This idea that if I draw this median and I draw this median, forget about line segment DE just for a moment, right? Then CP would be twice PD and BP would be twice PE. Okay, well, let me again draw these like little arcs in so that we really have got it here. All right, well, what do we know, right? What do we know at this point? We know that triangle DEP is similar to triangle CBP, all right? We just proved that. And this is key, right? We know that BC divided by DE is equal to 2, right? We know that BC divided by DE is equal to 2. We knew that way back in Unit 6, right? That BC was twice the length of DE. But we also know that in similar triangles, the ratios of corresponding sides are equal, right? So I can say that BP divided by PE, right, those two sides would correspond. I'm going to go from one double arc mark and the other double arc mark. I can say that BP divided by PE is equal to BC divided by DE, right? So the ratio of that to that has to be the ratio of this to this, but BC to DE is 2. Right? And that literally says BP is twice PE, right? I could then rewrite this BP equals 2 times PE. Likewise, right, I could now also go with the other set, which is that CP divided by PD, right, is equal to BC divided by DE. So CP divided by PD is equal to BC divided by DE, which is 2. And that will tell me that CP is twice PD. All right, forget about all the fancy fraction work and all of that, right? It boils down to this. This triangle and this triangle are similar. And since this side is twice the length of that side has to be twice the length of that side, and that side has to be twice the length of that side. And it just It's just similar triangles, right? That's all it is. Now granted, way back in Unit 6, we didn't have similar triangles. Back then, we actually proved that DE was half the length of BC by using a parallelogram and using CP/CTC proofs and things like that. But we did prove it back then. Essentially, again, this triangle is half the size of that one from its side length perspectives. All right, so let's now play around with this. Exercise number 3. In the following diagram, medians NR and OQ have been drawn and intersect at point C. If OC is equal to 18, then find the lengths of CQ and OQ. All right, so simple enough, right? OC is equal to 18, all right? We want to figure out the length of CQ, and we want to figure out the length of OQ, all right? Well, the whole point of partitioning, right, is that OC, right, to CQ is equal to 2 to 1, okay? In other words, OC is twice the length of CQ. So that should make it easy. CQ, right, then is 1/2 of our 18, and that's equal to 9, right? That's simple. And now, of course, OQ is very easy because OQ is simply OC plus CQ. So OQ is equal to 18 plus 9, which is equal to 27. Now, I want to point something out. Very important, right? CQ is 9, right? OC is 18, and OQ is 27, right? The shorter portion is 1/3 of the entire median. The longer portion, the portion that goes from the vertex to the centroid, is 2/3 of the entire length, right? So initially we have this 2 to 1 ratio, right? But that's a part to a part, if you will, part 1 to part 2, right? 2 to 1, part 1 to part 2. But that means the total is 3, right? So it really then boils down to part 1 to total equals 2 to 3, or 2/3, and part 2 to total equals 1 to 3, or 1/3. And that's extremely helpful then in part B. So let's take a look at that. If NR is equal to 36, find the lengths of NC and CR. So right, in this case, we're told that NR, the entire thing, is 36. All right, and we know that NC is twice CR. So I could set up, like, I could call that X and that 2X, and I could then solve for X. You shouldn't need to do that, right? One thing I know at this point is that NC to CR is 2 to 1, which means RC to NR is equal to 1 to 3, and NC to NR is equal to 2 to 3. All right, this one makes my life very easy, right? I can now say RC is equal to 1/3 times 36, which is 12, and CR, pretty easy too, right? Whoops, NCNR. No, that's not what I want. I wanted CR here. Sorry. No, that's right. Yeah, that's right. So now NC, my apologies, NC is equal to 2/3 of 36, which must be 24. Okay? So it's really, again, important to understand this. When I've got this 2 to 1 ratio, right, 2 to 1, then I can really think about this whole thing as being 3, and this being 1 to 3, and 2 to 3. And then that just allows me to use fractions and products to find those lengths if I have the totals already. Okay, let's take a look at one that's a little tricky. Exercise number 4. In triangle ABC, the median from A to side BC starts at A, -4, 10, and ends at D, 11, -8. Let point P be the centroid of triangle ABC. Determine the coordinates of point P. Show how you arrived at your answer. Well, I know that this would probably be a lot easier if we had a coordinate grid right now, okay? But again, I want you to just think about this for a second. I'm just going to draw a generic triangle, okay? Not to scale, not to orientation, nothing like that, all right? Let's just say I've got A, B, C, and I've got point D, right? I'm told that A is -4, 10. I'm told that D is 11, -8. And I'm told that the centroid is at point P, right? And I want to figure out what its coordinates are. Well, this really takes me back to our last lesson on directed line segments and partitioning them in the coordinate plane, right? Because I know right now that AP to PD, in this case, is 2 to 1, right? I know AP to PD is 2 to 1, right? So I know that AP, right, that P is 2/3 of the way from A to D, right? Point P must be located 2/3 of the way from my starting point to my midpoint over here. So I now need to just do that directed line segment work. See if you can figure out what the coordinates of point P are. All right, again, the idea is I'm going from A to D, so my delta x is going to be 11 minus -4, which is 15. My delta y is going to be -8 minus 10 for a whopping -18. And now I want to add 2/3 of those changes to point A in order to figure out where point P is. So the x of point P will be at -4 plus 2/3 of 15, which gives me -4 plus 10, or 6. And y of my partition point will be my starting y at 10 plus 2/3 times my change in y, and that will be 10 plus -12, and that will be -2. So my centroid is at 6, -2. What a wonderful combination of two lessons that we've seen, right? One lesson being how do we locate the centroid, right? And the fact that the centroid will be at this 2 to 1 ratio from the vertex to that midpoint, right? And then the other piece, you know, how do we find a partition point along a directed line segment in the coordinate plane? Okay, let's now take a look at constructing the centroid. So you can be asked using a straight edge to construct construct or to find the centroid. Compass and a ruler, compass and a straight edge, etc. The key is going to be to locate the midpoints of the sides of a triangle. All right, that's going to be the key, right? That's the only hard part, which is just finding those midpoints. All right, so first, let's just review how to find the midpoint of a line segment. Exercise number 5. Using only a compass and straight edge, locate the midpoint of segment AB shown below. Label it point M. Recall we do this by constructing the perpendicular bisector of AB. So the only real legitimate way of finding the midpoint or constructing the midpoint of a line segment is to construct the perpendicular bisector of the line segment, which clearly then goes through the midpoint. Now I know we've constructed a lot of perpendicular bisectors in this course, but let's review again how to do that. All right, what I'm going to do is first move my ruler out of the way. I'm going to bring my compass over here, putting down the center of my compass at point A, extending my compass so that it's more than half the length of the line segment, and then I've got to get this thing back onto the point A. I'm going to draw an arc here. I'm going to go below the line segment and draw another arc, hopefully again trying to stick that point there. Man, I tell you, sometimes this compass. All right, now I'm going to switch and put my compass point on B without changing the radius. Very important, right? Don't change the radius. And of course I missed, right? Very close. Close enough, I think. And then I'll do this. Just to be clear, it's really not particularly close enough. I really should get that arc to be a little bit longer so that I'm actually make an intersection point there. Oh my. This is taking longer than it should. There we go, that's better. All right, get rid of my compass. And now I just connect my two intersection points. And when I do that, it is the perpendicular bisector. I don't really care that it's perpendicular. All I really want is that midpoint, right? I've got to be able to locate midpoints in order to draw medians. I have to be able to draw medians in order to find their intersection point to find the centroid. Okay, so let's do it. Exercise number 6. Using only a compass and straight edge, locate the centroid of this triangle. Label it as point C. Leave all construction marks. Now, keep in mind, right, the 3 medians will all intersect at the same point. So you just have to draw 2 of them. You just have to construct 2 of them, which means I've got to find 2 midpoints. Any 2 midpoints, and then I draw their medians in. So if you like finding the midpoint of SR, I think that one's natural. And then finding the midpoint of QR, great. You want to do SR and SQ, great. You want to do SQ and QR, great. It doesn't matter. All right, why don't you pause the video now and see if you can locate the centroid of this triangle. All right, well, I think finding the perpendicular bisector or constructing the perpendicular bisector of SR makes a lot of sense because it's nice and long and it's horizontal and all that kind of stuff. So I'm going to first do that one. Maybe move my ruler out of the way for the time being. Get a nice arc up here. Come on, pencil. There we go. All right. And then I'll do the same arc down here. That ruler. Okay, come up here, reverse, bring it over here. Great. Bring it down here. Awesome. That'll be enough to find that perpendicular bisector and that median. Okay, draw the perpendicular bisector in. And again, the only purpose of that is to find this point. We'll draw the median in a second. I think what I'm going to now do is I'm going to do the perpendicular bisector, I think, of QR. Again, it doesn't matter whether you do QR or whatever. You just have to do 2 of them. That is really the key. You got to do 2. I'm going to maybe make that a bit bigger. Okay. So, come on, arc. There we go. There's my arc there. Rotate it below. These pictures get real messy. Sorry about that. And now I will flip, put my compass point at Q, draw that arc again. And I gotta rotate it up. Come on, where are you? Nope, okay. Rotate it down. Now I can use it. Oh, and my arc wasn't long enough again. Excuse me for that. I gotta flip it back over here and make this arc a bit longer. I'll just do that. There we go, that's good enough. And now, I can finally get that perpendicular bisector. And yes, you could be expected to do this. No worse than any of our other point of concurrency constructions, I think. There's my other midpoint. Now again, just for a moment, because we still have a little bit more work to do, right? Both of those two constructions served one and only one purpose, which was to find the midpoints of their sides. Now that I've got those midpoints, the rest is relatively easy. I just need to draw in two medians, one from point S going to that midpoint, right? So that's one of my medians. And then the other median, right, will go from point Q to the midpoint of SR, and that will be right there. Whoops. Close, come on. I need to tilt that a little bit more. Where those two medians intersect is my centroid, which is a little bit hard to see. And did they say label it point C. And there it is. Messy, messy, messy constructions, right? Because you've got to construct the two perpendicular bisectors of any two of the sides, right? Then just draw on the medians connecting the vertices with that median, with that midpoint, and then where they intersect is the centroid. Now a little side note on centroids. They're really, really quite cool because if you have a triangle and you actually find its centroid, all right, that will be the balance point of the triangle. You could literally cut the triangle out of paper, set it on your finger or on a pin or whatever, and that triangle would just balance perfectly. It wouldn't tilt to one side or another side. Another name for the centroid of a triangle is the center of mass, all right? And that's again because it's its perfect balance point. All right, so today we looked at the medians of a triangle and the fact that the three medians of a triangle have a common intersection point, also known as a point of concurrency, known as the centroid. The centroid then partitions any given median into a ratio of 2 to 1, specifically the distance from the vertex to the centroid is twice the distance from the centroid then to the midpoint of the opposite side, all right? That means, right, that we can, if given the length of a median, we can find the lengths of its individual partitioned portions. You could also, as we saw in that last exercise, be expected to actually construct the location of the centroid because you can construct the midpoints of any given segment. Therefore, you can draw in two medians. Okay, so this is kind of a cool topic. You definitely are going to get tested on it. They love you to know the fact that those medians get partitioned into 2 to 1 ratios. It's all due to similarity, as we saw in exercise number 2. So get some work on the homework on these ideas. For now, I just want to thank you for joining me for another geometry lesson by eMath Instruction. My name is Kirk Weiler, and until I see you again, keep thinking and keep solving problems.